In this video, we are going to take a look at the percent composition, empirical, and molecular formula notes and example problems. So first of all, percent composition is simply the percent by mass of each type of element in a compound. So if you divide up the mass and look at it based on what type of elements there are in the compound, the percentage of each element, that is the percent composition. So you take the mass of one element, total, divided by the mass of the total compound, which we also know is called the molar mass. This is a useful tool for identifying unknown samples. We have instruments that can give us the percent composition of a sample, and scientists can then use this percent composition data to determine what's called the empirical formula for the compound, which we will talk about in just a few minutes. So first, if we wanted to calculate the percent by mass or percent composition or mass percent of H2O, all those words mean the same thing, we first want to figure out what the total mass of the compound is. So I am going to write out the two elements. There's hydrogen in water and there's oxygen in water, and we want to know how many of each of these there are. And if we break apart the formula, you might notice that there are 2 hydrogens and 1 oxygen, because we know a missing subscript in chemistry indicates that there's an implied 1 in the formula. So 2 hydrogens multiplied by the molar mass of hydrogen, which I'm going to round to 1.00 or 1, so 1 gram per mole. And then oxygen's molar mass is 15.999, which I know I can round to 16 grams per mole. And so I'll get the mass of each individual component of water. The total mass of the hydrogen, 2 times 1 gram, gives us 2 grams coming from hydrogen. And then 1 times 16 grams gives us 16 grams coming from the oxygen. So I will sum these two together to get our total molar mass. The total molar mass of a water molecule is 16 plus 2, which is 18 grams per mole. But we actually want to have the mass percent of each of these compounds, and so instead of just leaving the molar mass alone, I'm going to take 2 grams of water and divide it by the 18 grams per mole, and do the same thing with 16 grams divided by the 18 grams per mole. And so when I do this, I will end up with the mass percents of water. So 2 divided by 18 gives me 11.1% hydrogen. And then 16 divided by 18 gives me 88.9% oxygen. And of course, I first got these in decimal format, but I immediately moved the decimal 2 times to the right to get, or to the left, I'm sorry. To the right, yes, I was right the first time. I immediately moved my decimal 2 times to the right to get them into percentage format, which is the same thing as multiplying by 100. Let's do the same thing for lithium phosphate. Now notice that lithium phosphate's formula is not given here, so the first thing we need to do is to crisscross to find the formula for lithium phosphate. So I'll take lithium, which has a +1 charge, phosphate, which has a -3 charge, and I'll crisscross to get Li3, PO4, and of course the 1 outside parentheses doesn't need to be shown here. So now I will break this apart into its elements so I can add up the total molar mass. We of course have lithium, and we have 3 lithiums, we have phosphorus, and we have oxygen. Now, because there is no subscript next to phosphorus, I know that that 1 is implied, and there's a subscript of 4 next to oxygen, so I know there are 4 oxygens and 1 phosphorus. Now we'll go ahead and fill in the mass of each individual element. We'll multiply by the number of that element. Lithium's mass on my periodic table says that it's 6.94 grams. Phosphorus's mass is 30.97 grams. And then oxygen's mass we know is 15.99, which I'm going to round to 16. So then I will multiply all these out. 3 times 6.94 gives me 20.82. That's the number of grams coming from lithium. Phosphorus's mass for the total amount of phosphorus is still just one phosphorus, so it's 30.97 grams. And then 16 times 4 for oxygen gives me 64 grams. And then, of course, to get the molar mass, we'll add those all together. The molar mass. It's 20.82 plus 30.97 plus 64 gives me 115.79 grams, 0.79 grams per mole for lithium phosphate. Now, to get the percent by mass, we are going to divide each of the individual masses by 115.79. And this time I'm just going to write it once. I'm going to put a big division sign here, divided by 115.79. And then we will get each of our individual mass percentages, and we'll write them over here. So 20.82 divided by 115.79, I got 0.1798, so that'll be 17.98%. 30.97 divided by 115.79 and times 100 to get it to a percent would be 26.75. And then 64 divided by 115.79 times 100 gives me 55.27%. And of course, all of our percentages should add up to 100%. So you can always check your work on these to make sure that your percentages add up to 100% total. That is the most important thing when rounding here. There's really no indication of how many sig figs our answers should have. So we just want to make sure that our percentages add up to exactly 100%. And we also should label what compound this is for, so 17.98% lithium, 26.75% phosphorus, and 55.27% oxygen. And that is our answer here, is all three of our percentages. So now let's talk about empirical and molecular formula. The empirical formula is the formula that shows the smallest whole number ratio of elements in a compound. And so we've seen empirical formulas before because for ionic compounds we always simplify to the smallest whole number ratio of the metal and non-metal that make up the ionic compound. And this is an empirical formula, but we can also write empirical formulas for covalent compounds just by simplifying down the formula. The molecular formula, on the other hand, is the formula that shows the actual number of elements in a compound. And as I stated, for covalent molecules, we usually show the formula as the molecular formula because many covalent compounds, while they have the same empirical formula, they can have very different molecular formulas, giving them very different properties. So for instance, this molecule right here is called benzene, and here is acetylene. And you can tell right away that these molecules look very different. Their structures are very different. Even if you know nothing about these two compounds, you can see that they look their formulas look different when written out this way. They do have different molecular formulas. Acetylene is C2H2, whereas benzene is C6H6. But if we were to simplify these down to their empirical formulas, 2 divided by 2 gives us CH, empirical formula, 1 carbon, 1 hydrogen. And 6 divided by 6 gives us CH as the empirical formula again. So the empirical formula is just showing the ratio of the elements that make up the compound. It is not showing the actual number of each element in the compound. And that's important to note when moving forward. Now, this idea of empirical and molecular formula is important for determining the identity of an unknown sample. We can take percent composition data that's collected by some sort of instrument, and we can use that percent composition data to get to an empirical formula with a simple process. And there's a little rhyme to help you remember the process. It goes like this: percent to mass, mass to mole, divide by small, multiply till whole. And if you can remember that rhyme, then you can remember all of the steps for going from percent composition data to an empirical formula. And I'm going to demonstrate that process for you now. So our first step here is literally just to take the percentages that are given in the problem, 82.8% carbon and 17.2% hydrogen, and convert them into grams. So we're just going to change the percent sign to a gram sign. So we're going to write out our two elements, carbon and hydrogen, and then we're going to put 82.8 grams of carbon and 17.2 grams of hydrogen. And that is our percent to mass step. That's all we have to do for that first step here. Pretty easy start. And I go ahead and make my table because I'm going to have more conversions coming in this problem. We've done our percent to mass step. Now we're going to convert our mass into moles. And to do that, all we need to do is set up our dimensional analysis and divide by the molar mass of each of these elements. And we are talking about the elemental molar mass here. Because our elements are making up a covalent molecule, they are not in their pure substance form, we are not considering the fact of whether or not an element is a diatomic element. So 1 mole of hydrogen is equal to approximately 1 gram of hydrogen, and 1 mole of carbon is equal to approximately 12.01 grams. And even though we usually would round hydrogen's mass to 1 gram, in empirical formula problems, it is generally best to hold on to more sig figs than you normally would. So I'm going to go ahead and put in 1.008 as my mass for hydrogen. Then I'm going to get my number of moles for each of my two substances. This is our mass to moles step. So when I multiply this out and divide, I get 6.894 moles of carbon, and I get 17.063 moles of hydrogen. So we've done our mass to mole step. The next step is divide by small. And what this means is we're going to pick the smaller number of moles that we've gotten, and we're going to divide both of the number of moles by that same number to get a quantity known as the mole ratio. I'm going to do this step in a different color. Now my smaller number of moles is 6.894, so we're going to divide both of these by 6.894. Divide by 6.894. So of course this first value is going to become 1, and my next value is going to be 2.475. So that's my divide by small step, and this quantity is known as the mole ratio. Now, to write our chemical formula, our empirical formula, we can't have a decimal quantity. The smallest whole number ratio has to be whole numbers by definition. And so this last step, multiply till whole, means that we need to multiply our mole ratio quantities by a integer that gets them both to whole numbers. And so we want to look at what decimal this is close to, basically, to 1 decimal place. And we're looking for a couple things here. So if we have something that's 0.23 or 0.27, those are awfully close to 0.25, anywhere in this range, which is approximately 1/4. So if we were to multiply one of these to whole, we'd probably multiply by 4 to get it back to a whole number. If instead you're looking at something that's between 0.31 and 0.34, that's pretty close to 1/3. And so we'd probably multiply these by 3 to get them to a whole number. So you just have to use a little bit of judgment here. If we have something that's between 0.47 and 0.53, 3 or 5,2, it's about a half, so we'd multiply by 2 to get back to a whole number. And so you kind of have to look and use your judgment here. 2.475 is awfully close to 2.5, so I'm going to multiply both my quantities by 2 to get them to whole numbers. So 1 times 2 of course gives me 2, and 2.475 times 2 gives me right about 5. And so that gets them to whole numbers. It's 4.95 really, but that is very, very close to 5. And so then these are the numbers that make up my empirical formula. So I have 2 carbons, so C2, and then 5 hydrogens, H5. C2H5 is my empirical formula. Empirical. It's always important to label these because we do have a big difference between an empirical formula and a molecular formula. Now, last but not least, we want to convert our empirical formula to the actual molecular formula for our compound. To do this, we need to know the molar mass of the compound itself. So that piece of information is given here. It says the molar mass of butane is actually 58.1 grams per mole. What is the molecular formula? And it's giving us a reminder that we already figured out the empirical formula is C2H5. Basically, what we need to do is figure out how many times the mass of the empirical formula will go into the mass of the molecular formula. So our empirical formula has 2 carbons and 5 hydrogens. So we need to figure out the total mass. 2 times 12, and I can round here because I'm just looking for an approximate value. Gives us about 24 grams coming from carbon, and 5 times 1 gives me about 5 grams coming from hydrogen. So if we add that up, the mass of our empirical formula is about 29 grams per mole. That's for our empirical formula. Now, our molecular formula, it says, has a mass of 58.1 grams per mole. So I want to figure out how many times the empirical formula is my molecular formula. So 58.1 divided by 29 gives me right about 2. So that means that my molecular formula is 2 times my empirical formula. So we'll take that C2H5 and we're going to multiply that by 2 to get our molecular formula. So that means my molecular formula is C4H10. We're just multiplying the subscripts by 2, and that is our molecular formula for butane.